would equal K sub 2 concentration, where did my O go to? Concentration of O3 raised to the first power, concentration of O raised to the first power. Okay, and this would be rate 1. And we would give this the symbol K1. Okay, so there's our rate 1 and our rate 2. Now, if we add these two reactions together, we get the overall reaction, which is going to be, and I'm going to steal here, copy, paste. We're going to have 2 O3s going to 3 O2s. So notice that oxygen, the single atom is made in that step, and it's used up in that step. So single oxygen atoms here would be a reaction intermediate. Okay? Now, when we look at any reaction mechanism, when we have multiple steps, there's always one step that is going to be slower than all the rest. You've experienced this if you've ever baked a cake. Usually your slow step is baking the cake. Mixing up the batter is not that time consuming, but baking it is. Okay? Think about traffic. We all know about construction, road construction in Tuscaloosa. When they pinch it down to one lane, it limits how fast you can move along the roadway. Okay? In a reaction mechanism, the step that is the slowest step in the process is called the rate determining step. Okay? And the rate law for the rate determining step must match the experimental rate law for the mechanisms to be considered possible. Okay, let me say that again. In a reaction mechanism, the slowest step is called the rate determining step. And the rate law for the rate determining step must match the experimental rate law for the overall reaction for the mechanism to be considered possible. So let's look at this energy diagram. So if we really think about it, each step in the process, okay, has its own activation energy. The slow step, the rate determining step, is the step that has the largest activation energy. Okay? So let's look at the mechanism up here. I'm going to copy it and bring it down. Copy. Paste. Okay? So when we're looking at a mechanism to see if the mechanism is any good, we want the sum of the elementary steps to sum up to the overall reactions, and we want the rate law for the mechanism's slow step to be consistent with the experimental rate law. Now, let's add to this. Okay? I'm looking at example problem 14.9. We're told that the experimental rate law is rate equals K, the concentration of ozone raised to the second power concentration of oxygen, O2, raised to the -1 power. Now guys, this is an unusual one for us because we haven't looked at any rate laws where we've had a product in the rate law, and we haven't looked at any with a negative exponent. But that's okay with what we're working with. Okay? Now, anytime we are given a reaction mechanism, there's always a step that's slow. At this point in your scientific career, you can't identify the slow step. It's going to have to be given to us. In this reaction, the slow step is the second step. Okay? The second step is the slow step. Now, if I look at the rate law here for the second step, one of the things I want you to notice is that rate law contains a reaction intermediate, oxygen. I can't compare this against the experimental rate law because it contains a reaction intermediate. I can't just give up and throw my hands up in the air and walk away. What I have to do is I have to look at this first step. Okay? This step is going to come to equilibrium waiting on the second step to happen. Now, I'm going to put a double set of arrows in here. The double set of arrows means that this sucker comes to equilibrium. So this step comes to equilibrium. I'm just going to use EQ, waiting on the slow step. So come back to this one and say, well, no, I'll go ahead. So when we look at the slow step and it comes to equilibrium, it means, we'll go ahead. Rate of the slow step forward equals rate of, not slow step, rate of, in this case, step 1 forward has to equal rate of step 1 reverse. The definition of equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. Okay? Now, rate 1 forward. And I'll call it 1F, is going to equal K sub 1, concentration of O3, okay, rate 1 reverse is rate 1R for reverse is equal to K 1R concentration of O2 times the concentration of O. Now, these two have to equal each other. Okay, so I'm going to set them equal to each other. Now, I'm going to solve this for oxygen concentration. If I do that, I'm going to divide through by this. I've got K1 O3 concentration divided by K1 reverse O2 concentration, and that's going to equal oxygen concentration. Let me get rid of the underline here. Okay? Now, what does that allow us to do? Well, now I have a way to replace the concentration of oxygen atoms in the rate 2 with things that appear in the overall reaction. So if I come down here, I can write rate 2 is equal to, let me copy, paste. Now, where the oxygen is, I'm going to replace it with all of this. And let me copy and get rid of that and hit paste. Now, get rid of that. Okay, so now I have a constant. It should be K2. K2 times K1 divided by K1 reverse. That's just a new constant. So I'm just going to call it K prime. And then I'm going to have O3 times O3. So that's going to be the concentration of O3 squared. And then if I think about it, an O2 on the bottom is the same as having it raised to the -1 power. Okay. Let me make sure that none of that is underlined. And I get this. So I get rate 2 is equal to K prime, concentration of O3 squared, concentration of oxygen to the first power. If I compare that against the experimental rate law, okay, which we have up here, notice they match. So what we can say at this point is that this mechanism is possible. Okay? Now, there are a couple of other examples I've got here for you. One is where the first step of the mechanism is a slow step. So if I looked at the reaction 2NO2 plus an F2 going to 2NO2F with the rate law, rate equals KNO2 times the concentration of F2, and the mechanism was a two-step mechanism, okay, where NO2 plus F2 goes to an NO2F plus an F, which is our slow step, followed by a fast step, NO2 plus F going to an N2F. And we looked at the rate law for our slow step and compared it to the experimental rate law, okay? They match. So this tells us that our mechanism is possible, and we would try to trap a fluorine atom to prove it. This one we started out with, where the slow step was the second step, that's the hard case. Okay? Now, here's another example. So I've already worked one through with you. I expect you to be able to work through this one on your own. Okay, I've got it out here for you. And then look at problem 76, 75 on page 631 to get more practice. Last thing in the chapter is mention a catalyst. It's a substance that increases the rate of the reaction but is not consumed by the reaction. A catalyst works in the reaction by changing the reaction pathway. In other words, it alters the reaction mechanism. And doing so lowers the activation energy of one or more of the steps so that the whole process will go faster. So let's look at an example here. Okay, here's a reaction, and here's the original uncatalyzed reaction pathway. See how high the activation energy is? It happened in a single collision event. The catalytic pathway, or the one with a catalyst, actually happens in 2 steps, and the activation energy of both of those steps is much lower than the activation energy uncatalyzed. So it lowered the activation energy and it increased the rate of the reaction. And that ends chapter 14.